Welcome to the Designing a LIDAR Application with Mentor Optiwave using the HHI PDK webinar. Things we're going to go over today. First, we'll talk about the Mentor Photonics tools, and then I'll hand it over to HHI to discuss their PDK and their foundry solutions. And finally, Optiwave will talk about their solutions with a demo, and then at the very end, we'll have Q&A. Feel free to submit your questions as the webinar commences. So with our solution, here's our proposed, basically our design flow. We start with schematic capture. This is our SEdit product. This works directly with the OptiSPICE solution. And then we can drive right into our LEdit Photonics product, which is our full custom layout editor with photonic options. And then that we can feed that directly back into OptiSPICE as well. On the other side of the flow here, we have our LightSuite Photonic file. This is our automated solution. This is for large scale designs, 100 and plus more active components. And that can also be worked directly with the OptiSPICE simulator for verifying that result. Everything else is built on top of the Calibre industry leading verification products, which are DRC and LVS. And how that flow applies to different methodologies for our designers and users. First, we have the layout-centric flow. This is really where we see about 90% of our customers right now in the photonics design space, is they're working exclusively with LEdit Photonics, the layout flow, and then they're driving simulation directly from LEdit Photonics without actually using a schematic in this case. So with our flow, we just drive directly into OptiSPICE from LEdit Photonics, and then verification happens with everything in Calibre DRC. Some of our users are moving to where they want to use a schematic-driven approach. Basically, they want to quickly realize their circuits in a schematic without having to have all the detailed waveguide routing, and be able to simulate and verify that the design is working correctly before starting layout. So you start with your schematic here, you drive directly into OptiSPICE, verify that the design is going to execute at the design parameters you need, and then you start LEdit Photonics and basically run the schematic-driven layout flow. Finalize your layout in LEdit Photonics, run DRC, and in some cases, some of our customers are starting to use LVS to verify that the schematic and the layout match, and then verify everything with OptiSPICE. We also provide a script-driven flow. This is with our LightSuite Photonic Compiler solution. This is for large-scale designs where you're dealing with a lot of optical components and a lot of electrical routing to control those optical components. This is used using Calibre real-time to verify all that execution in the script. Then finally, you do your final verification and layout LEdit Photonics with both DRC and then driving OptiSPICE to verify your design. We also support the schematic-driven approach with our LightSuite Photonic Compiler. So again, you start with your schematic, you drive your circuit in OptiSPICE, verify the circuit is working correctly, then drive LightSuite Photonic Compiler to do all the automation and scripting. And then final chip assembly again in LEdit Photonics with Calibre, DRC, and LVS. All these flows are built on top of the HHI PDK. With regarding to LEdit Photonics, this is our full custom solution. This is again where most of our customers in photonics are working. They're designing all their photonic circuits in LEdit. This is again based on top of the LEdit full custom editor. So you have your full capability of an any angle editor to do any types of design you need. And then what we've added is a set of photonic features that make it easier, more productive for photonic designers to get their day-to-day jobs done. Some of those features are waveguide creation, crossing insertion, snapping, as well as pin checking. And then we've exported the circuit into OptiSPICE to do your verification, so you don't have to worry about validating your design. With our waveguide routing, basically we allow our customers to stay highly productive by doing simple orthogonal path creation using all the capabilities that LEdit has for path creation. stretching, not extending, snapping, etc. And then with a single command, you turn that orthogonal path into a waveguide. The waveguide here is a hierarchical P-cell, and what it's doing is taking full advantage of the HHI PDK components, bends, straights, S-bends, etc., to draw an accurate P-cell using those foundry delivered PDK components. Once it's at this hierarchical level, we offer some control for users that want to control a little bit more detail about the hierarchical P-cell, like the radius of the bend. Let's say you wanted to modify the default radius, you can change it here to make it larger if you need to. S-bends, etc. The type, what waveguide type you want to use from the HHI PDK. And then finally length. If your waveguide has a trombone section, you can have it automatically extend or reduce that length of your overall waveguide with the trombone section in order for waveguide matching or offset in simple designs like an interferometer, for example. We offer snapping. This is really important in the photonic design space because there's a lot of photonic components that are quite large compared to the size of the optical photonic waveguide routing. And so having to zoom in and out is cumbersome and problematic. So what we've added is a simple snapping feature, which automatically snaps your orthogonal path that you started with to the nearest pin, and then you convert it to your waveguide without having to worry about any alignment issues at that pin, which could result in power loss. LIDAR supports various scripting languages, Tickle and C, as well as Python. So a lot of our Python customers are familiar with a lot of our photonic customers are familiar with the Python language. And so now LIDAR supports the ability to manipulate your design with macro creation, etc., with Python scripting. You have full support of all, so you can import additional Python modules for complex output or input. Like let's say you wanted to integrate with Excel and output a bunch of data from your design, your layout design, and then you have access to all the UPI calls or internal calls to LEDs to manipulate data with Python. Now I'd like to hand it over to HHI to discuss their Foundry and PDK offering. Thank you.
Thanks, Alan, for the introduction. Hello, everyone. I'm Durvasa, a PhD student at Fraunhofer-Heinrich Institute. This presentation will be about the Foundry services for photonic integrated circuits that we've offered since a number of years now at Fraunhofer-HHI here in Berlin. Particularly, those Foundry services are on indium phosphide photonic integrated circuits. So what we're doing since 2016 is very much an analogy to what the electronics industry has pioneered already in the 80s, namely multi-project wafer runs, also called shuttle runs. The idea clearly being you share the wafer and you share the cost. This is a pretty established business model in electronics, but in photonics, for the most part, people still develop custom technologies for their respective products, which is something we're trying to change using a generic photonic integration technology and 3-5 technology at that. This generic technology has building blocks, just like in the case of electronics. We have an optical amplifier building blocks, which is analogous to a transistor, a phase modulator for a resistor, and so on. The important point to be noted is that it is possible to have gain sections with indium phosphide. So the generation, manipulation, and detection of signal can all be done on a single chip. Having such building blocks separates the design from the process, and customers can develop circuits from the provided process development kit or PDK. So we have the technology in place now that uses indium phosphide and its related quaternaries. I will later touch upon it briefly to give an idea on the wide range of functionalities that are possible on a single chip. And of course, when you do this as a foundry, you're not alone. You have to fit into an ecosystem of number of software vendors, namely players like Mentor Graphics, that are extremely helpful in this space to us because they offer tools that allow us to encapsulate all functionalities into process design kits, PDKs, that enable layout generation for our customers. And This is integrated with OptiSPICE, which is a Tanner plugin for circuit simulations from the company Optiwave. OptiSPICE drives compact model libraries that are then useful for circuit level simulations for our customers. What you see here on the right side is a screenshot of the Mentor PDK and LIDAR. Alan has already talked about it, and in the next section, Jem would talk more on OptiSPICE. We not only work with Mentor Graphics and Optiwave, but also with a number of layout vendors, of course, so that people can choose from a variety like NASCAR or Synopsys to create the mask files using specific PDKs to match our requirements so we can manufacture a chip right away. Just to give you an idea, we're doing this on a commercial basis now since 2016, and we already successfully fabricated for over 100 customers. And many customers order more than one integrated circuit, so the number of circuits we have made has really grown. And that's something that would really not be possible if we wouldn't go for a generic technology. If you were to develop a new technology for each of those customers, then of course, over 90% of those customers would have to opt out due to the cost. So it's very easy to prototype using such a technology. And what all is included in our technology? I'm not going to go into too much details, but I'll just give you an overview of what we can do with our technology. On your left-hand side, you see a cross-section through all the technology. It consists of two different quantum well stacks for the actives. One for the strong electro-optic effect using the quantum confined Strach effect. Those are purple. They're sandwiched in a PN junction, and in red, you can see the ones that are used for gain. The blue layers, which light propagates, this is indicated with the transparent gray line. Those are the passive waveguide layers, which are ion doped, so they form a semi-insulating layer. So by making use of the pin structure, photodetectors can be realized. With this configuration, you can have not only regular detectors, but also balanced detectors. And crucially, you have low loss RF routing because the substrate and the waveguide layers are not doped. So that gives you a wide variety of building blocks. As you can see on the right-hand side of the table, we offer a number of couplers. We are pretty proud to say that we offer full polarization functionality, namely polarization rotation and splitting. On the active side, we also have a number of components. We have tunable gratings, we have SOAs, we have DFB lasers, DBR lasers, we have electro-absorption and electro-optic modulators, Mach-Zehnders and photodiodes, as well as the necessary routing for DC and RF signals. If you want further details or specifications of any of the components, you can ask me in the Q&A at the end, or you can contact me later. Next, I'd like to show you two examples of what customers did in the past using this technology. A nice design that shows the power of large-scale integration in indium phosphide is an all-optical neuron. This was designed, tested, and engineered by Princeton University and published in 2018. Here, they basically use the nonlinear dynamics of a DFB laser to model a neuron, namely the activation function of neurons. How it works is you have a train of optical pulses which are detected by a photodetector, and this photodetector outputs its electrical current into the bias of a DFB laser. The DFB laser itself is biased just below threshold, so you can easily kick it above threshold if you just supply enough current. However, it is biased such that a short spike of electrical current that is generated by just one optical pulse is not enough. But if you have several pulses in rapid succession, then they would basically be integrated by the laser, and the laser goes above threshold and starts lasing for a short amount of time. Then it gets a spike. That's exactly the kind of behavior that you would expect from a neuron. It's strongly nonlinear and it rapidly activates given enough input and doesn't do anything if your input is below threshold. Nice thing is this device is completely optical. It has some electrical processing inside, but from the outside world, it looks like an all-optical neuron. The second example I want to show you is a nanosecond wavelength switch, which was published by Microsoft last year. Nice thing here is you can use SOA, semiconductor optical amplifiers, as gates to rapidly switch on and off an optical signal. So for access networks, for example, instead of using tunable lasers to address the different subscribers, for which you'll have to wait a long time to reconfigure the optical wavelength, because tunable lasers are rather slow in tuning, you can have a set grid of necessary wavelengths available all the time and go into this wavelength division multiplexing configuration on your photonic integrated circuit and just bias whichever SOA and whichever channel you want to operate right now. So in this way, you can easily get below 1 nanosecond switching speed from wavelength to wavelength. And implementing this in the photonic integrated circuit as opposed to discrete benchtop components, you only get like 3.5 dB implementation penalty as reported by Microsoft UK. Okay, this is something we just announced in 2020. We just released what we call PIConnect. So our customers oftentimes struggle when they receive their chips to do the electro-optic characterization. So at least for the electrical part, we now offer quite a nice solution. So this main board that you see on the left-hand side integrates a number of laser drivers, 16 source meters, the temperature controller, and so on, which can be controlled rather trivially with the graphical user interface and the supply drivers. And we can assemble this with a ribbon cable together with your optical chip. We wire bond it, and so once you have a chip, you can start doing a test right away. So if any of this interests you, you might ask yourself how to get started and how does all this work in practice? Well, our broker is JPEX in Netherlands. You either reach out to them or to us directly. You'll be in once you sign a user agreement, which can be downloaded from the website jpex.eu. You will then be supplied with the PDK of the respective software vendor you want to design in and the design manual. Then you submit your design. After a fabrication time, which is currently around 4 months, you get your chips and you can either do the testing yourself or with something like PIConnect, or go to one of our testing partners and you have a proven prototype in a time frame of around 6 months, which again is something completely unheard of if you don't go for a generic technology. So you can really evaluate your idea super quick. Okay, that's it for me. Thank you very much. And Sham will take over from here to talk about Optiwave and to demonstrate the LIDAR application.
Hello, thank you for the introduction. Today, I'll be talking to you about the collaboration we did with Mentor Graphics and HHI to be able to support photonic integrated circuit design flow. But before we get there, I'll be talking a little bit about our products, and then I'll introduce you to our product that we integrated with Mentor Graphics. It's called OptiSPICE Plugin. And then finally, I'll be doing a demo. During the demo, I'll be going over various aspects of our integration. So here we have a basic company overview. Optiwave was established in 1994 as a spin-off from National Optics Institute in Quebec. We're currently located in Ottawa, Canada. Optiwave offers a wide range of software for designing components, links, systems, and networks. Our products help users shorten their design cycles, improve product quality, and cost effectiveness. Because Optiwave has been around for so long, we have been able to sell thousands of copies of our software to businesses, universities, research, and governmental institutions. We make business with over than 80 countries worldwide. Here you can see the type of businesses we cater to, starting from photonic component and module suppliers, optical telecom equipment providers, telecom service providers, defense contractors, nonprofit organizations, and universities. Optiwave offers a wide range of products going from system and circuit level to component level. And we have a new product called OptiInstrument, which is at the instrumentation level. At the system and circuit level, we have OptiSystem and OptiSPICE. OptiSystem is our best-selling product. It is mainly used for designing transmission systems. OptiSPICE is the product we're going to talk about the most today. We have two versions of OptiSPICE. One is a standalone OptiSPICE, which is designed for supporting photonic integrated circuit simulation for both electrical and electro-optic devices. We also have a plug-in version of OptiSPICE, where it is capable of integrating with other EDA tools. In this webinar today, we'll be talking about OptiSPICE's integration with Mentor Graphics Tanner. At the component level, we have OptiBPM and OptiFTTD for designing waveguide devices. We also have OptiGrating for designing gratings and OptiFiber for designing and optimizing optical fibers. OptiInstrument is our newest software. It is designed to remotely control test equipment. So what you can do with it is you can set up parameters remotely. You can automate your experiments and then collect the data and extract this data and post-process it. We're also planning on integrating this with photonic system and simulation tools like OptiSystem. Now let's talk about OptiSPICE plugin. OptiSPICE was designed to integrate directly into other SPICE engines. It includes a set of compact model libraries designed to support photonic integrated circuit design flow. The main advantage is the capability of simulating optics and electronics at the same time. So whichever EDA tool you're using, you get access to the powerful optical simulation capabilities of OptiSPICE and powerful electronic simulation capabilities of the native EDA tool you're using. During the demo, I'll show you how we have integrated OptiSPICE compact model library into the Tanner EDA, and then we use this library for photonic integrated simulation of a LIDAR chip. There are two ways you can use the compact model library. One is directly from mask, or you can also use the SEdit schematic editor so that you can build your schematics without having to worry about the mask layout. Another important aspect of photonic integrated circuit design flow is the PDKs. We have multiple collaborations going on with various photonic fabs, and we're going to demonstrate how we work with HHI to build a compact model library for their PDK and create a LIDAR design. Currently, in the Tanner plugin package, we offer an optical model library, which is based on OptiSPICE. All the devices in this library are documented, and they're also used in the tutorials. This model library supports multiple design flows, so you can use either the GPIC, which is the standard optical library coming with Tanner, or you can use our own basic native library with SEdit to build your schematics. We also have a series of application examples showing how to use these devices. Here we have a basic design flowchart showing how you can run Tanner and OptiSPICE at the same time for photonic integrated circuit simulations. In Tanner, you can do your photonic mask layout and then extract a netlist for the particular design. Once you have a netlist, you can build a symbol for SEdit and then use that symbol in a test bench. So in the test bench, you can use OptiSPICE devices to create a stimulus for your optical chip. The alternative is starting from SEdit and doing your design in a schematic and optimizing it directly from simulation. You can create your schematic using PDK devices and then run your simulations. Once you optimize your design, then you can either directly go to LEdit and do the mask layout, or you can actually create the mask layout from SEdit by running SDL. During the demo, I'll be showing you the OptiSPICE Tanner package. It already comes pre-installed with the latest version of Tanner. I will be running optical simulation with SEdit, and I'll show you how you can do the setup for the simulation. Then we'll look at the LIDAR mask layout and we'll talk about a little bit on how the design works. And finally, I'll show you how to generate a test bench from symbols from LEdit. Now let's start our demo with SEdit. On the left side, you can see the symbol library for OptiSPICE. This symbol library includes a set of basic building blocks that can be used either standalone to build prototype circuits, or they can be used in the test bench when you're extracting your netlist from the LEdit layout. In the schematic, you see these building blocks used to create a Mach-Zehnder modulator device. And these devices are also combined with standard SEdit devices. So we have, for example, a voltage source, we have resistor, alongside laser, photodetector, waveguide and phase shifters, and Y branches. Like any other electrical device, the parameters for these devices can be controlled by clicking on them and looking at their properties. So for example, for this laser, you can change the channel value or the frequency over here. As you can see, it is very easy to get your design ideas on the canvas. For example, you can go ahead and create a new schematic. Let's call this a demo. And then drag and drop your devices. Let's put a laser here and a photodiode. And then we can connect these devices together through wires very easily. And while you're dragging the wire, if you right click, actually, it will snap to the port. Once you've done your design, you can go ahead and do the setup for the simulation. We support the DC operating point analysis, transient, and AC analysis. You can also do parameter sweeps. So all you need to do is select one of these and then decide your stop time and time step, and then you can go ahead and run your simulations. Now let's go look at a few examples. These examples on the left that you see, they come pre-installed with our model library, OptiSPICE devices. And as I said, you can do frequency and time domain analysis. So this circuit is set up as a Mach-Zehnder modulator. We can do the frequency analysis on it by clicking Start Simulation. Once you hit simulation, a netlist is created, and then T-Spice is called alongside OptiSPICE so that we can run optical and electrical simulations. So this is, as you can see, the frequency domain solution for the Mach-Zehnder modulator. Now let's look at how this design works in transient analysis. So we have replaced the DC voltage sources with voltage pulses. These are coming from the built-in Mentor Graphics Tanner libraries. Again, all you need to do is hit Start Simulation, and the results will pop up in the waveform viewer. There we go. You can also do more sophisticated simulations. For example, we have a filter demux simulation. So here we have a multi-channel simulation where each laser is set to a different frequency, and then all these signals are converging into one single waveguide, and then on the other side, they're filtered based on the channel. Here we're using an ideal optical filter, where you can set the center frequency, either bandpass or bandstop, and the bandwidth, and the frequencies will be filtered based on that. You can also design a demux with ring resonators. One of the main advantages of OptiSPICE, as I mentioned before, is the ability to do electro-optic circuits, and specifically, it is very good at handling feedback loops. So this is a relatively large design for simulating a fiber optic gyroscope. So what happens here is we have forward and reverse traveling signals in this ring resonator in the middle. And then the frequency shift due to the rotation can be calculated using balance detectors and a control circuit. So what happens is, as the rotation rate changes, the resonant frequency for the forward and reverse propagating waves change. So we use the control circuit to make sure that the signal going into this ring resonator tracks the incoming frequency, so the resonant frequency of the ring. So by tracking the resonant frequency changes in the ring, then this circuit is able to track the rotation rate. One other advantage of using T-Spice as a simulation engine is you get all the abilities that comes with it. For example, here we have a PID controller, which is made using Verilog. Now let's start looking into LIDAR and how we can extract netlist from a mask layout. Here we have the LIDAR chip that we have optimized. Before going on and showing you how to extract the netlist, I would like to show you some of the features of LIDAR we have used for the layout. One of the things you can do with LIDAR is actually easily do your waveguide routing. So here I'm just drawing a basic wire. Now, the next step when you're drawing waveguides is actually doing a snap to port. There we go. Now we can turn this waveguide with this wire into a waveguide from tools and generate auto waveguide. Now let's go and edit the features of this. Now we can select different types of waveguides. Here we need E1700, and let's click OK. There we go. So our waveguide is created. There are a few things. So you can turn this back into a wire and change different types. They get routed. So for us, we need E1700, so I'll put it back. The other thing you can do is you can change the band radius. So let's change this to 150 maybe. And there you go. Now let's go ahead and extract our netlist. You go to Tools, Photonic Tools, Extract Netlist. It needs to be extracted as subcircuit. We have already chosen a name and a location for it over here. Click OK. It's been extracted. So let's go and open it. So here you see the LIDAR chip extracted. Now let's copy this because we're going to need it soon for building the symbol. Now that we have extracted our netlist, we can build our symbol. To do that, you need to first go ahead and create a new view. Let's call this LIDAR chip SP. It needs to be a SPICE view. And then we need to paste the netlist we extracted into here. Once we do that, the next step is going to cell, generate symbol, and then set up the location of the ports. For example, let's say we want 2 ports on the left side. We would write port 1, port 2 here. So these port names need to match the port names that are defined in the subcircuit. We have already one defined here, so I'm not going to go through, but I'll show you the resulting symbol. Here's the resulting symbol. Finally, you can use this in your test bench. Now let's talk a little bit about the basics of this chip and then look at our simulation results. The laser is producing the reference signal, which is then divided into two paths. One path is sending the signal out to the target, and the target is modeled as a mirror over here. And the signal is reflected from the target and then sent back to the MMI. And then inside the chip, we have the reference signal that is interfered with the reflected signal. And then these signals combine together through the MMI and then sent to the balance detectors. So the result of the balance detectors is a beat signal, which then can be used to determine the target, the distance from the target. So now let's go ahead and run the simulation. Here we get a beat frequency. Let's zoom in and we can use the markers to do the measurements. Let's move this here. And then this. So the frequency is about 200 megahertz. Now let's go and look at the simulation results from the chip itself that we extracted from the netlist. Again, you can see the inside of the chip is modeled by the extracted netlist, and the externals of the chip are still modeled by OptiSPICE devices. Again, you can just hit run and look at the simulation results. Now we can zoom in and look at the frequency, the beat frequency detected. Yes, this is about 200 megahertz as well. So our simulation results match in both cases. So this ends my presentation. Thank you very much for listening. I also would like to let you know that we're actively looking for fab partners for adding additional PDK support with OptiSPICE. So if you're interested, please feel free to reach us from our emails. And thank you very much for listening.